Good morning, guys. So, we will be having our demonstration for FTIR. So, that is Fourier transform infrared spectrometer. First of all, my name is Gokarneswar Sahu. I am a teacher in the Department of Chemistry, and my specialization is organic chemistry. Of course, if you know little bit about pharmaceutical chemistry, so that is our specialization. We do research on those topics, and we use this FTIR every day because our characterization of molecules is based on this. And one more equipment you will be learning is nuclear magnetic resonance. Okay, I think that is on 27th. So now about this FTIR, first of all, of course, you see this lab is our special instrumentation lab 2. So because here you can see many other equipment, very expensive and very useful equipment we have housed here, because you all saw that we removed our shoes, so we don't make this room dirty or dusty, because these equipment are very sensitive, and that's why we try to maintain the cleanliness of this room and as well as the temperature, because many of these you can see the little bit sounds and they all emit heat. So to maintain the heat, we have ACs. Of course, in winter we don't need in Rourkela, but in summer we need. So coming to this FTIR, my plan is to have one demonstration. Of course, we have Subhadip Giri. He is a trained technician for this spectrometer as well as NMR. So he will help us also in the operation of this one, and we'll do 2 samples. Of course, you have got 1 sample from your side, 3 samples we will do. Basically, I try to do 2 types of samples. One is in solution and the other one is solid. So you will see how we do those samples. And after all this operation, and you see that how you are getting the spectrum for your sample, then if we have time, we will go to our seminar room and I will explain how do we analyze the spectrum to get the information what we need. So now Subhadip, can you please help us in explaining this?
This is ATR Pro. ATR means attenuated total reflectance.
This equipment cost 15 lakhs. Of course, depends on other advanced accessories, but still this one is enough for characterization of all molecules what we need. Yes.
Sample chamber.
I think everybody can see here, because you guys don't need, or should we make batches? एक बार में कर दें या हाफ हाफ करके? Who? They? Okay. You guys maybe can come this side. So now the one we are putting here, this is the you can call the sample holder. Now we put the sample here, and everything else like the source which will give infrared, because again I will be talking there that what is the principle of this one. This is based on infrared electromagnetic radiation. You know electromagnetic radiation, like the one we see, which radiation this is? This is visible, right? So besides this visible region, there are several other, starting from gamma ray, X-ray, ultraviolet ray, then visible, then infrared, microwave, radio wave, and so on. Okay, so it consists of several regions of electromagnetic radiation, and why it has been divided into different regions, because researchers have seen that molecule interacts differently in these regions. Visible regions, we are able to see it. But if some molecule they absorb ultraviolet, we cannot see it, because our eye cannot process that wavelength. Okay, so only we can see visible. So similarly, infrared, this is something, it involves in vibration. There's something interesting about the discovery of IR, when I forgot the name, it is there in my slide. So what he was doing, through prism, prism, what you do, if you pass sunlight, you will see these 7 colors, right? But when he was doing, there is Vibgyor. So what he found, after red, that surface got heated. So when it's heating or anything happening, there must be some change, and that change is because of interaction of that surface with infrared region. That's why he named it infrared, after red. Okay, so that vibration, that electromagnetic radiation makes the molecule vibrate. Okay, so that's why that information we get it from here. So please carry on, and then we will talk more in the little bit theory. So now you can see here, it's very difficult. So he tried to now put the place where we will put our sample in the spectrometer. So now we will put our sample, and after putting our sample, the infrared will go and interact with the molecule, and then we will get the spectrum there. So that is just to operate all the information what we are getting. I am covering this one? Oh, sorry. Okay, so she is my PhD student, Ms. Sukanya Mandal. So she got 2 samples, because we also did that experiment yesterday to see everything is working fine. Maybe step by step we can tell. So now the software which we will analyze, now we open that software, and basically now you see what is happening here. In air, what we have? Carbon dioxide, oxygen, nitrogen, and so on. So when we are making one sample, there is also air, right? So, and in air, if you don't know, maybe we will talk in the slides, that there is something which will absorb IR, electromagnetic radiation, and that is carbon dioxide. And greenhouse effect. What is that gas which causes greenhouse effect? Carbon dioxide. And what is that effect? Yeah? It warms our atmosphere. That's why carbon dioxide is something which can absorb infrared. And if it absorbs, it can keep our surface or our atmosphere warm, because Earth was not at this temperature at the beginning. It was very, very cold. Life was not possible. But because of this carbon dioxide, greenhouse effect, now it is considered a bad effect, because it leads to global warming. But initially it was a good effect. Greenhouse effect is a good effect. And why it is so? Because with trees they release carbon dioxide, and slowly we had enough concentration of carbon dioxide so that our atmosphere is warm and life is possible. Okay, so that's why carbon dioxide is the only gas which absorbs this IR, electromagnetic radiation, and keeps our atmosphere warm. And to avoid that carbon dioxide, what we always do, we do the absorption of sample and one background. Background means there you don't have your sample. That means the carbon dioxide or in any air that will be absorbing the IR radiation in the blank. And what we do, we take our sample and deduct that absorption by carbon dioxide from the blank. Are you getting? So then whatever information we get, that is because of our only sample. So now you see he is doing the background scan. You will see something, you see this one. So there is no sample, but you see some peaks are already there. That is because of, even we have moisture. In air we have moisture. We might have sulfur dioxide, we might have, now the pollution is so high, we might have some other chemical in gas form. So now that will all lead to this one. So this is something, this will be subtracted from the information from our sample. Okay. You can always ask questions if there is any confusion. Okay. So now you see that is something we got, and we will place our sample now, right? Or you are waiting? Okay. So you see without the sample we got something, and that is not our information which we need. We need only the absorption by the sample, by the molecule we are providing. Okay. So yeah, so now you see what we are trying to do. Okay, maybe थोड़ा उस तरफ ले सकते हैं उसको, थोड़ा just, because then I can accommodate here so that everybody can see. Yeah. Okay. So now there is a place where the IR radiation will come. You can see there. Yeah. So now what we are trying to do is make a thin film. Okay, because the normal way what we take, we make a solution. We take our compound and in organic solvent, we make the solution, and that one we put in there. But now there is the question, because the solvent also will absorb IR. So for that what we do, we use a volatile solvent, which evaporates easily. So now we put it and let it for some time, so the solvent will be evaporated. Now when the solvent is evaporated, now a thin film. So that's why the concentration should be maintained properly, so that the thin film is not so thin that it will not absorb enough IR radiation. Okay. So it is sometimes fine, you can have 1 milligram of your sample. Okay. If you take that in maybe 100 microliter, that is enough, and you can put the sample here. And again, if you don't get a good okay, we have already got the spectrum there. If you don't get a good spectrum, you can always put another drop. Okay. So you can just go on with that one, but only if it is too high concentration, the peaks will not be sharp. Okay. But that can be experimented, that doesn't cost much. You can always do that one. So now you see what he did. Okay, those guys are not interested. So what we did is first we take the blank scan. Blank means we don't have our compound. So anything else, any gas in the air, or if some impurity also there, anything. So that will give a peak there. But we are not interested in that peak, remember. Then what we do after the blank scan, we will do another, we will put our compound. First one we are doing in solution. So that means you make a solution, I told maybe 1 milligram in 100 microliter or something. So that solution, just take a drop and put on that place here. Okay. So when we put there, now you let it evaporate, because otherwise the solvent, almost all solvents are IR active. So that solvent peak will come there. We don't want that one. So we let that solvent to evaporate. Now after that one, maybe next time again we can do another scanning. So, you will see once it is scanned, now you got the spectrum. So, these are all the peaks, from your compound. Okay. Now, I will tell you how this thing is happening. Basically all spectroscopic methods. Spectroscopic methods means they use electromagnetic radiation, I told, from gamma ray to radio waves. Okay. So, what we do that there is always source, which source will give gamma ray, which source will give UV, which source will give IR, there are sources. So, in all spectrometers you have a source where or which will give electromagnetic radiation. If it is IR spectrometer, it will give IR. If there is our UV spectrometer, it will give UV. Okay. We have NMR there. When we discuss that one, it gives radio wave. Okay. So, now what we do, we have the information that what wavelength, what intensity we have given the source. Okay. Now, what we do, we put our molecule in between. So, when we put our molecule, this electromagnetic radiation and the molecule, they will interact. So, in this interaction, the molecule will absorb some amount of the radiation you are giving. Okay. So, this is all what is the principle of spectroscopic method. So, once the molecule absorbs, now the rest will pass, which is not absorbed, that will pass, and that energy will be detected by another equipment, that is called detector. Okay. So, the detector will take the electromagnetic radiation which is not absorbed by the molecule. So, now once you have given something and you got something, now you know which part of the radiation is absorbed. Now, that will be processed, and that process will be coming as a spectrometer. That is all techniques used, and then here what we will be discussing, that how we analyze, because all these peaks, they have some meaning. Okay, they are, for example, now if I for example, you see this is in centimeter inverse. Centimeter inverse means what? Wave number, right? Wavelength is centimeter, or you can call it nanometer or whatever it is. Then wave number is centimeter inverse, or if you go to frequency, it is in hertz. Okay, in NMR we will see. So, now you see from let us say how much it is, 3600, it is 400, right. So, 4000 to 400 centimeter inverse. So, now the energy which is given is 4000 centimeter inverse to 400 centimeter. So, now you see here the percentage transmittance T. So, that means here when it is at the top, nothing is absorbed, everything is passed, right. Some around here, let us say 3300. Now, you see what is there, this transmittance is low. Can you see? Because here, okay, it is not 100%, but around 90%. But here, it is how much? Maybe 85%. Here, it is how much? Maybe 50%. So, the transmittance is 50%. That means it has been absorbed by the molecule. That is how you get a peak. So, if nothing is observed, then you should get something a straight line. But when it is observed, now the transmittance is low. Transmittance is inversely proportional to absorbance, right. So, that means whenever you are getting a peak, at that centimeter inverse, the energy is absorbed by the molecule. Very simple principle, that you give something, your molecule will interact and will absorb, and the rest will be passed. So, whatever is observed, that will obtain as a peak. Now you need to learn, what is this IR spectroscopy, which part of your molecule will give peak in what region and so on. So then you can analyze the spectrum. For example, if I think you may not know, so there is a peak at around 1600, maybe 1700 something. Okay, now he will do the peak picking. Just I think right click or something. Yes. So now you see what we did automatically, these are all advancements in spectrometers. So now it gave the peaks, wherever there is a dip, you just give that the lowest point, that what centimeter inverse is that. So in that centimeter inverse, your molecule has a absorption. Okay. For example, something when I discussed that 1712, that is known for carbonyl absorption. Okay. So that means which this compound is methyl ester. So okay. So now this one is a ester compound. So if it is a ester compound, we know that this is the range where we will have the carbonyl frequency. Okay. Similarly, we have all this. Now again, if we talk about this IR spectroscopy, the whole region is divided into two parts. What are the two parts? One part they call from 1400 to 4000, and then from 400 to 1400. I think this is very nice that when we have the spectrum in front of you. So what is that region? Something you can see from 1400 to 4000, there are less number of peaks.
Sir, why 14,000 to 600, why not 18,000 to 400?
I will tell you. So from 1400 to 4000, you can see the peaks are not so many. But from 1400 to 400, you see it is very clumsy, right? So what is that called? That this part is called fingerprint region, and this is called functional group region. Okay. Now coming to why it is called fingerprint, fingerprint, where it is used? In crimes, right? In crimes that expert people come and then they study this fingerprint. And the idea is no two human has similar fingerprints, and that is exactly true for this, that no two molecules have the same spectrum in this region. Okay. But again if you make the comparison, this fingerprint, in case of crimes, can we solve? No. Experts has to come. And similarly here, if we want to solve this, somebody has to be an expert to find that every peak is for which part of your molecule, which is very, very difficult. Okay. That's why mostly most people they study from 1400 to 4000, where the peaks are less, and that is for functional region. For example, you must know ketone, aldehyde, ester. What is the functional group there? The carbonyl. Okay. And the carbonyl, for example, here it comes at 7012. And mostly we are many times involved in the identification of functional group. What is a functional group again? What is that?
Protein summit band.
Yeah, what is that? Exactly why that is called a functional group? If I take decanol, there is OH, so the functional group is OH. But then whatever this C10, and then there will be H2 also 20 or more than 20. That is not called the functional group. Why? Because the function of the molecule, the property of the molecule is because of that point, that hydroxyl point. Okay. So the molecule functions by that group. That's why it is called a functional group. And mostly, for example, you told protein, they are amide bonds. We are interested about the amide bonds. So, that is what they occur in this region. So, because they occur in this region, mostly the use of IR spectrometer is because of understanding of the functional group region, not the fingerprint region. But again, if you are interested, you can always analyze to get more information from the fingerprint region. You had one question, what was that?
Sir, why this peak or not from
Yeah.
1800?
So, now for example, if you say 1800 to 4000, now for example, here carbonyl, many functional groups, they have, for example, carbonyl, alkene, alkyne, they all come in the region of 1400 to 1800. So, if you skip that portion, you are losing so many functional groups in many organic compounds. Okay? So, it is not a strict rule that you don't go beyond 1400. It is just that in this region it has been found that many functional groups, you talk about olefins, you talk about alkynes, ketones, or in that broad peak is coming because of hydroxyl, because of CH and so on. So, they all come after 1400. Okay. So, you study that one and it is mostly informative that we get all data from that region. Okay. So, now once you get this, of course, it is now easy that you export this, you can show that one. So, we get our IR spectrum of the compound given there. So, now we need to clean it and use your sample, then of course, maybe this sample we can use because this is small compound, the peaks will be less. Okay. So, now if you have solid, you do not need to make a solution. So, what you do, just take a pinch of the compound and put on that place, and again you see I told that it should be a uniform film. So, to make the solid, because you are taking a lump and when you put it, it may not be uniform. So, now we have this one, so we press down. So, when you press down, hopefully that will make a uniform film, that solid compound. So, that is what we will be trying. Now, let us see. Okay, नाइट्रोबेंजाल्डिहाइड इतना जरूरी है थोड़ा, हाँ देखो देखो जितना डालना है. So, we can clean it afterwards. So, there is a very small point. So, try to put your solid on top of it, because if you put everywhere except that, you will not have a good spectrum. So, now he put it as another sample, and so you can see there. Okay. So, now he pressed exactly where this IR radiation is coming. So, he pressed that one, mostly it will be uniform because we have applied pressure. So, now it has pressed the solid sample, and okay. So, now the scanning is going on. We can make the base correction also. May not so. Okay. 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 So, now you see the spectrum is different than what we did last time. So, we use the solid compound, everything is same, only the operation. There we put the solution, let it evaporate, but here there is no such thing. We just took our compound, put on there, and remember it has to be pressed. The reason behind that is to make a thin film and homogeneous, because then it will absorb with equal intensity. Okay. So, now again you can see all these compounds came, this is because of this technical error, nothing to worry, because this should be like this. It happens, always there will be technical errors, and okay, nothing to worry about, because this is definitely not a peak. You can see the peaks like this. Yes, there is peak and these peaks are there. Again, you should be interested after 1400. So, these are the regions which shows that what kind of functional groups you have. That is something we will discuss in the with the slides I have. Okay. So, maybe we can do their sample. So, what is this compound? Hello, what is this compound here? Huh? Sorry? Okay. So, let us see, because of course, I think it will be having so many peaks, because these are complex molecules. For example, we use very small organic molecules, maybe 300, 400 molecular weight, but these molecules will have very high molecular weight. High molecular weight means several, several bonds. So, it will have very clumsy, but let us see. So, now there is a question, which samples you cannot study in IR spectrum? From all these explanations, what do you think that which samples you cannot study?
Which cannot absorb IR radiation.
Which, okay, that is a good point. So, which cannot absorb then? Higher molecular weight. No, that is something you will see. If the molecular weight is higher, of course, it has nothing to do with the molecular weight, it has to do with every bond. For example, water, we have two OH bond. Yes, yes. For example, ethanol. So, in ethanol, what are there? Of course, OH bond, carbon oxygen bond, carbon carbon bond, carbon hydrogen bond. So, these peaks are for all those bonds. Please remember, nothing to do with the molecular weight. It is how many bonds are present in the molecule. Okay. Big molecule, so many bonds. So, not necessarily if molecular weight is high, it will not come, it will come here. Okay. So, only thing you will find that if the atoms are bigger, for example, let us say potassium bromide, okay. We need to show that pellet also. Okay. Potassium bromide, potassium and bromine, they are bigger atoms, not like carbon, hydrogen, oxygen, nitrogen, they are bigger atom. So, when you have bigger atom, that bond, this KBr bond, that absorbs in very low energy. There is a term reduced mass. So, if the mass is higher, the energy is lower, because it is like the every bond you can think like a spring, they are attached with a spring. So, if it is a spring, you can always vibrate it. Okay, and that is exactly that happens in the molecule. So, when this vibration occurs, it absorbs the IR radiation. Okay. So, if it is very big, then it will absorb below 400, that we cannot study. Otherwise, every and each molecule we can study in IR spectrometer. Okay. It is little bit crystalline, nahi?
crystalline
हाँ.
है, flaked.
Let's see. उसका ऊपर वाला क्लीन की. Yeah, you can put just FPE.
External sample.
हाँ ठीक है. No, hello. This sample, you have any idea what are the functional groups or what is the structure? No. Acetyl. Okay. Okay. So anyway, I'll explain. Now you see what is the difference in those samples and this sample. I'll tell you. Okay. Now this is the spectrum. What you see? Yes, what you see in, if you compare the earlier two spectrum and this spectrum, it is not clear, right? It is, there were sharp peaks, but here the peaks are not sharp. So now from this I can definitely say whatever molecule is this, it's a huge molecule. Now huge molecule means it has so many bonds, maybe thousands or 10,000, 20,000 bonds are there, and all those 20,000 bonds will absorb. Now that is what it is leading to merging of several peaks. Okay. So when try to think that let's say in this region you have 3 peaks, so they will be coming sharp. In this region there are 300 peaks. What will happen? They will merge, and that is exactly happening with this molecule. That it is such a huge molecule, you don't get individual peaks, but you get peaks merging on each other. And it is very, very difficult to characterize. But again, to understand this one, you can always maintain the concentration, maybe take dilute compound, okay, find where it is soluble, take this compound and make it is very, very dilute and see if you can get sharp peaks. But at least we are getting something in around, yes, 1651, 70, because he was telling it is acetyl. Acetyl means there is carbonyl. Okay. So carbonyl means you can see there is coming 1743. Okay. And then there is a sharp peak as 2360 and so on. So few of the functional groups at least we can characterize by this FTIR spectrometer. Okay. Maybe we can show that KBr pellet and okay. Sorry. Now I will show you there is another way we can do this experiment is use of potassium bromide. I just told potassium bromide, it is so heavy that it does not absorb in this region. So now what is done is you take potassium bromide, it is a solid compound, you know sodium chloride which is salt. Similarly, potassium bromide is another salt. So you take your compound, mix with potassium bromide, you really grind it, make it uniform, and then we have this pellet. Yes. So we can show here. So this is where we will make the pellet. Again I told we need to make it uniform. So when we are using potassium bromide and our compound, we need to make, it is a solid mixture. In solution everything is uniform, but when we are making solid mixture, if you do not grind it properly, it will not be uniform. So you take in mortar and pestle, properly grind it, try to make it uniform and then convert that solid into a thin film, and that is what it is here. we can apply pressure. When we apply pressure, that solid mixture will turn into a thin film, okay, and that we can use. We have yeah. So here, okay. So now you see, yeah. All these techniques. So what we do, we make the place ready. For example, here, yes. So now here we put our compound, that solid mixture. Okay. So when we put our solid mixture, then to make the film, we put this one. Okay. So now between this and this, there will be the solid mixture. Okay. So now we put in there and give pressure. I think if you understand, this is a simple thing, but to make that film a good quality one, so this is all techniques have been used. Maybe you can press with hand, that might work, but just to have it very, very uniform, this pressure is applied and we get the film, and then just again you take this out, you remove this one, and that film you use. We have the sample holder. Yes. So now here, okay. So there, you put it there. Okay. So now in this we put that thin film, because of course mostly it will have this size, right, after pressing. So now that one will be pressed here, and we remove that whatever we used to put the sample on top. Now we put it vertically, and IR radiation will pass from there to here, and then similar thing it will absorb and you will get the spectrum here. So at least there are three ways. One is you use solution and put it there, let it dry, and you get the spectrum. The other one is solid. You put the solid, press it, make it a thin film, get the spectrum. And then the other one is through potassium bromide pellet. Okay, mixed with potassium bromide, because potassium bromide doesn't absorb in this region we are studying. That's why potassium bromide is used. And once you make the solid mixture, then you make it a thin film here and study there. Again you get the spectrum like that, and that can be studied. Okay, so after this, any question you have?
Practical explanation.
Sorry?
Practical application.
Practical application. Okay. So the so this instrument is something used for chemical analysis. That's why you guys are coming to chemistry department. So chemical analysis. Chemical analysis means everything what we do is because of a certain compound. We all are wearing something. They are having different colors. That is all because of some organic molecule in the material. So when you want to study, I have actually given many lectures in food processing department, how the structure contributes to the taste of your molecule, taste of food, to the food getting bad. I mean, for the when this for example brinjal, I always present that one. You cut the brinjal, I mean after some time you see the color is turning brown, right? Why the color is turning brown? Yes, oh, he is my student. I told you who answered. Okay, because it oxidizes. There are phenolic compounds. Okay, so phenolic compounds are prone to get oxidized. Which oxidizes phenol? Aerial oxygen. Enzyme cannot oxidize. Enzyme needs oxygen to oxidize, and that aerial oxygen is there plenty, so that will oxidize. You know, that's why to not get that brown color, what your mother does, they put the brinjal in water, so that oxygen cannot reach there and it will remain fresh. Okay, so all this I give so many structures of berries, blackberry, blueberry, there are, not in India but in abroad countries. There are few berries which are poisonous. If you eat, you will fall ill, and if you eat in bigger quantity, your life is at risk, because there is a cyanide functional group there. So with time, that cyanide is, cyanide is poisonous. So now once that concentration increases in our body, we will fall sick. So all these properties, taste, stability, that is because of the structure of molecule. Now to understand the structure of molecule, we have this. We have NMR spectrometer. You will see, for example, Madhuresh sir, Professor Madhuresh Dwivedi, we are doing some collaboration. He wants to study the concentration of ethanol in some of the extract he is doing. I think his student, if he is there, here. Palm tree, okay. So now, how do you know what is the concentration of ethanol? So he brings sample, we do analysis, and we know that how ethanol will be characterized in NMR spectrometer. Now we tell him that, okay, this is the concentration of ethanol in this sample. Now he brings another sample, there we see if the concentration is higher or lower. Now for example, he collects the sample 1 day, after 2 days, after 3 days. Now if we see the ethanol concentration in first day is less than in second day, is less than in third day, that means with increasing day, the fermentation is going higher. Now let us say we study for 20 days. Now we will see that maybe after some days, maybe 5 days, the concentration is not increasing. That means the fermentation process is stopped. So that is the use of chemistry in food processing, that we understand the structure of your material, of your food, and characterize that what is occurring in this process, if the food stays longer, if the food gets destroyed earlier, all these properties we can study by correlating the organic molecule in your compound by all these spectrometers. Did I answer your question? Okay, so that is what it is. Basically, you see the chemical structure of your material. Now, whatever you are studying, you try to correlate that with the structure of your molecule. Yeah, any more question?
Sir, we got the data from the spectra, but how we can analyze that particular field?
So that for that one, if that is the last question, we can go to our seminar room. I will have a small presentation, not in very detail, but briefly I will show you that how we can analyze this spectrum. Any other question than that one? Because that is something I will answer in the seminar room. Is that all? So then we can go to our seminar room. The second floor, I think Sukanya can take everyone. Seminar room. Okay? Okay guys, so see you there. So now I will just, of course, this is pure chemistry, but I will not discuss in very big detail, but how do we analyze? Okay, so we learned how the spectrum can come out, but then we will see how it is analyzed. These are just some introduction, we will not go there. Yeah, for example, here you can see this carbon dioxide. Yes, carbon dioxide, how it absorbs, because vibration, you can see here, when there is vibration, carbon, each carbon oxygen bond, they are all meant to be vibrate, means the bond will be longer or smaller. So, when it happens, it absorbs electromagnetic radiation. So, you can see here different regions of electromagnetic radiation. We have gamma ray, we have radio wave. So, now the energy from here, when we go to this region, the energy increases. So, that means all this type, gamma ray, X-ray, UV visible, infrared, what we are studying, or microwave and radio wave we will be discussing in NMR spectroscopy, that these, they interact with molecules differently. Again, all these energies are given. You can talk about the frequency, you can talk about the wavelength, or you can talk about the wave number that varies for different region. So, this is just yeah. So, now this is again the basic principle. What it is? Your molecule. Just think about, of course, you can think about your material, food and other things, but they have molecule. Okay? And think about that molecule, always they remain in the ground state, the most stable state. And when we give energy, for example, infrared, now they go from ground state to excited state. They, you see this is electromagnetic radiation, for example, IR. So, when we give IR, the molecule from here goes here by absorbing this energy. So, when it absorbs this energy, now we study that what energy was absorbed and how much energy was absorbed. That will give you the spectrum, and that spectrum is analyzed. For example, here we have given that what kind of interaction it does. Where is IR? Yeah, it is here. Energy gap created due to vibrational motion. Okay. The molecule, again, if you think about carbon dioxide or water, there is a OH bond, and it is considered like O and H are connected to the two ends of a spring. So, when it is a spring, they can come closer, they can go away. When this happens, there is a energy difference. Yeah, so this is all given, the different kind of motions and different kind of energy, gamma ray, X-ray, visible and so on. We will not go in detail, I am here to only give you what happens. So, this is one rotational spectrum which we are not studying. Now, next one is something you saw in IR spectrum. This is what is. And now, after that, you can get UV spectrum. Yes, you can get UV spectrum. So, now if you compare this, something you can see, this is very thin. Now, if I go higher, this is little broad, and then if I go higher, this is very broad. Okay? And the energies, if you see, this is higher energy, this is lower than UV, and this one is lower than IR. Now, the reason is here that electronic level, this is ground state, excited state somewhere it will be here. So, in one electronic level, there are so many vibrational levels. In one vibrational level, there are so many rotational levels. Okay? So, that means when there is transition, electronic energy, it can transit between several vibrational energy. For vibrational, it can happen, or it can, the transition can occur between several rotational. That is why when you are going from this spectrum to this spectrum to this spectrum, the peak gets broader and broader. Nothing to worry, because probably you will not be working on this analysis part, but just to have some idea that how it is analyzed. This is something what I have worked and then how I have characterized. We have taken, these guys, they work with thousands of molecules. Every day we take NMR, we take IR, we take our mass spectrometer, and from there all the information finally gives you that what is your molecule. This is what is one of the pictures. Yeah, for example, you can see here I have given functional group region and fingerprint region. Okay, the energies are there. Yes, it is here now. Probably you can understand here. So this is a molecule, carbon. There are two more bonds and there are two another bonds. So now what it says that each bond is like a spring. Okay. So spring means think about this and this. So they can come closer or they can go away. So when that happens, that is called a vibration, and it is the vibrations are two types: stretching vibration, if you stretch it or compress it, and then there will be bending vibration. Bending means you have the bond, now you bend it. Okay. So different depending on how you stretch, there can be symmetric stretching, means both in the same direction, and asymmetric stretching, both in the opposite. You stretch this one, compress this one. It is just naming of different kind of vibrational motions. This one is bending. Now again just naming. In plane bending, that means you have two bonds in a plane. So for example, these two bonds, you consider these two bonds. So like this, like this. This is in plane bending. So sorry. This in plane bending means there are again two types. One is both in the same direction. This is scissoring. You know how a scissor works, like this. Okay, so like this. Or if it is in the like this, then this is rocking. Just again naming. But what is important here is those different vibrations, they give IR spectrum, IR peaks. And then bending of vibration out of plane. What is this? This is the plane now. Now out of plane means this one. Okay, this went here, this went there. Or it can be like this, like this. So there are again wagging or twisting. Now twisting, this is, twist. When you twist something, this is. So the more importantly, forget about the naming, but there are this many possible ways. That's what I told, that fingerprint region. Those regions, they have all these peaks. So that's why you get several peaks, and mostly they merge on each other to give bigger peaks, not sharp peaks. Then again equations, somebody mentioned about bigger molecules. No, it is about only those two atoms bonded to the, two atoms attached to the bond. So M1, M2. Now you see this is reduced mass. If it is higher, then this will be smaller. For example, potassium bromide, we are using for making the sample. That means we can never use anything which will absorb in the region, and potassium bromide doesn't. That's why we use it, because potassium and bromine, they are relatively bigger atoms. At least bromine is such a bigger atom, this value will be so high that the wave number, this is wave number inversely proportional, it will be very small. Okay. Now let's go forward. Yeah, so now this is all little bit of chemistry, how it is happening. We have defined simple alkane. I think you all know alkane. You have double bond, you have triple bond. So now you see, when single bond, it's weak spring, double bond, strong spring, triple bond, very strong spring. Now if it is very strong, you see the energy 2150. I think you can feel it, that if the spring is very strong, you need to apply more force to vibrate. So this is well understood that if we have a peak at 2150, think about those peaks we got. If something is at 2150, you think that your molecule has a triple bond. If it is at 1650, you have a double bond. Now again you think about this 1400 I told. After 1400 these two are coming, right? Before 1400 this is coming, because you take any molecule, there are so many carbon-carbon bonds. You don't need to identify that one. But if you have olefin, you characterize because it is coming after 1400. If you have 2150, it is coming after 1400. So you characterize that one. Something you realize in the very left side, there is a broad peak, small one but very like this. We can see also if you have spectrum. Now that is all for CH. And in any molecule, how many CH you have? So many, right? So all CH are coming, it's not exactly 3000, it can come 3000, 3010, 3005, 2000, 2995. So all of them are mixing to give a broad peak, because there are so many CH bonds in any molecule. And if it is bigger, there are so many, the number is higher. Then there are all this hybridization, no need to worry about it. Again, here you can see peaks, some were big, some were small. You saw that one, right? Some were very big, the transmitters was very, very low. Like carbonyl we saw around 40-50%. But then there were some 80%, 70%, 60%. So when it happens, now it says that dipole moment. Okay. So dipole moment means what? Let's say carbon oxygen, carbon nitrogen, carbon oxygen, which is a strong dipole, or how do you know? The electronegativity difference, the periodic table. Yes, periodic table, think about periodic, periodic table is the biggest table for chemistry people. If we understand that, we understand probably everything. So if the electronegativity difference is high, then it is a strong dipole, for example carbon oxygen, then carbon nitrogen. So if any bond, again we are talking about the bond. So the two atoms, if the difference is high, then that is a the dipole moment is high. If dipole moment is high, the peak height will be big. Okay. Carbon, no difference, you will not get any peak. Carbon, nitrogen, small difference, you will get a medium peak. Okay. So all these heights, that's what I told. After doing that one, if we discuss this, you will get little bit of things. So all these heights are depending upon the two atoms bonded to that particular bond. Okay. So you get different. Then many things, alkanes, if we have alkenes, so lot of chemistry, we really don't need to think about it. These are all little bit of chemistry thing. Now you can see here a compound for this alcohol. I think I told 3, 4, 7, 8. So this is octanol. Now you see in this region, for example, the compound you gave, okay, it was little bit like this, because there are not many functional groups. Okay. But here you see there is a very strong peak for OH. That is what you see. And after that you see the CH stretching. So in this molecule there are so many CH, there is one OH, then there is bending frequency, stretching frequency, and so on. Okay. So this is how you get. Of course then there is, if you have OH, they make hydrogen bond. Further study, IR spectroscopy not only characterization molecule, it will also study that any kind of reaction. What is that one? OH makes hydrogen bonding. Now if you want to know how much hydrogen bonding is there, you can study here. Okay. So you dilute it, you make concentrated solution, you see the intensity of this peak will be different. So, if the intensity is different, then you study that how much hydrogen bonding, because if you take a dilute solution, the hydrogen bonding will be less and the peak will be sharper. Okay. So, there are in fact so many things here. Carbonyl, you see they are around 1700, 1750, 712. Then there is also small difference from 1810 to 1600. Different anhydride, acid halide, anhydride, ester, aldehyde, ketone. This small difference is enough to tell you that what different functional. All are carbonyl. All are carbonyl. But in that we have different carbon, which is someone is acid, someone is acid chloride, someone is acid amide, but they will give at a different value. Okay. Because you ask that how do we analyze, because this all information is already there, it is already known, it is there in the book, it has been studied. So, once we understand this thing, then we can analyze. Again another spectrum there, yeah, it is just so many, maybe I will go to the yes. So, here is the instrumentation, how it is happening. So, hot wire, I told infrared spectrometer causes heating. Okay. So, now if you heat something, it will give you infrared radiation. So, that is the source. Now, it goes IR radiation, it is there in the spectrometer. Now, it is divided into two parts. I told we are doing some blank scanning. Okay. So, this one it goes and then the reference cell. Reference cell means not everything without the compound. For example, sometimes what people do, they think about that one, we are putting the solution and let it dry. But if you do not want to dry it, so what you do, you take your solution and here you take your solvent, do not take the compound. So, the solvent will the solvent will absorb, here solvent will absorb and compound also will absorb. So, now finally what you do, you subtract, then you get what radiation was observed only by your compound. Okay. So, now it is divided into, the source is divided into two portions, one is reference cell. Now, let us say you are taking pure compound. So, there is air, here it is air, there is air, and in addition to air you have your compound. Okay. So, you do that one and then finally it comes, again it comes here. So, finally the sample information will be subtracted with reference information. So, you get only the information or radiation observed because of your molecule. So, now that will come here, the detector, it will now detect your which energy is transmitted. Now, it will analyze and give you the spectrum. Now, something, okay. So, there you can see which was there before. The spectrometer is dispersive infrared spectrometer. Now, what is there? It is all same, Fourier transform infrared spectrometer, FTIR. Now, this Fourier transform, it is in fact used for all spectrometers. Fourier transform UV spectrometer, Fourier transform NMR spectrometer. So, what is the difference? The difference is that this is the advanced version. Now, I will give you again example. You are scanning from 400 to 4000 centimeter inverse, right, the spectrum. In earlier spectrometer, what it was or how it was running, you give 400 to 450 centimeter inverse first. You see it is observed or not. You give 450 to 500 centimeters. You see it is observed or not. 500 to 550, 550 to 600, 600 to, now like that you go from 400 to 4000 and you can imagine how much time it will take. Getting my point? Individually you give all this IR frequency sequentially. anything. You go UV spectrometer, you go NMR spectrometer, the earlier days this was there. But now this Fourier transform came that you give from 400 to 4000 centimeter annual. The whole range you give at once. You see how much it took, probably 5 seconds or 1 minute maybe, because it was just doing the scanning. In 1 minute you are getting the full spectrum, but it was not possible in earlier spectrometer because you have to change or you have to give each range. If you want to get good spectrum, you give 400 to 410, 410 to 420, 420 to 430, because individually you have to analyze whether that was observed or not. I hope you all are getting. But when you give 400 to 4000, now what will happen? Let's go to one compound peak. Yes. Now we are giving 400 to 4000 at once. So this molecule will observe, this part will observe, this part will observe, all this. So when the detector will find, it will just find the rest one. Now this Fourier transform is a mathematical expression that will find out individual energies observed. Again to repeat, which was done individually before, now even if you are getting mixture of information, this Fourier transform can able to identify each energy separately. Okay? So you get the information in total, but that FT it will make it separate. Okay? So that's why this technique is used, which makes the scanning so fast than dispersive infrared spectrometer. It was done individually. Okay, so I think then we can. I really didn't want to discuss all this. That is our chemistry people's job. But this is how you can see that how we can, analyze the or how you can perform the IR scanning and analysis. And of course, this analysis is based on your understanding of IR spectrum, but ultimately once you understand, then you can interpret the spectrum efficiently to get the compound.
Good afternoon, everyone. In this session, we will discuss about the working principle of DSC. And what is DSC? DSC is the differential scanning calorimeter. Then why it is called differential? Actually, this instrument measures the difference in the heat flow between the sample and the reference with respect to the temperature or time. Then scanning. Scanning means your sample is scanned at a controlled temperature rate. Then comes to calorimeter. Calorimeter is nothing but a device which is used to measure the heat changes. Heat changes means there are so many thermal events like your melting, crystallization, and glass transition, and decomposition of the given sample. Then the model is here DSC 200 F3 Maya. Okay. Then come to working principle. This is your furnace. Okay. There are two slots are there. In one pan we are putting the sample only, and in another pan is your only empty pan. And both pan are subjected to a controlled temperature range. That means same controlled temperature. We will set the temperature at a controlled rate. Okay. Then inside the instrument there is a microcontroller. Okay. Microcontroller and a heating sensor. Then here we'll set the program and give the instruction to the microcontroller, and the microcontroller will give instruction to the sensor. Then accordingly the furnace will work. And why we are using the DSC? What is the application of DSC? Okay, and this is widely used in the field of polymer and environmental engineering and pharmaceutical engineering and food science and your agriculture engineering and biomedical engineering also, then cosmetic engineering you can say. And now we'll see how we'll put the sample and all. See, this is your crucible. You can see. This is your lid means cover, and this is your crucible. Here we can put the sample. And this crucible and the lid is made up of aluminum, and the maximum range of this is 600 degrees Celsius. This sample. Now we'll put the sample. Sorry. Now it is showing 26 and the pan itself is 23. The sample weight is 3 mg. And this is your hand press device. With the help of this, we will seal the pan. Now see, this is your furnace, and this slot is your for your sample, and this is for your reference. This is empty pan. So we put the sample over here.
This will measure the difference between the control and the sample.
Yes. And now come to the software part. Here you see, this is your measurement type is your sample. You will give all the data. Sample name will be what? Sample name.
Hydrogen, CHI TO SAM.
and your sample mass is 3 mg. Then here you see we are using the nitrogen gas. Here you see flow rate is 60, and the nitrogen gas is used for only protection for the chamber only. Okay. And here you see the temperature program. Now the temperature of the furnace is 22.8. Okay. We'll start at 20 degrees Celsius. Then your dynamic is nothing but your temperature will increase or decrease with respect to your time. Here end temperature will be 200. 200? 200. Here we will set the rate, heating rate. Your heating rate will be 10. Okay. Only heating, na? And now we'll start the program. Can you on this? First on that, You come to this side.
It should be 5 bar. One.
Now we'll start the program. Okay. Here you see there is a difference in the temperature, and there is a threshold. Threshold is 5 degrees Celsius. When it will reach, then it will start. Now you see this graph is called thermogram. Here you see this is your DAC axis, and this is your temperature, and y axis is your time. This graph is called thermogram. This is the data before we have saved it before, and see this is actually this is your thermogram. Okay, and here you can see two peaks are there. One is this is what? This is endothermic or exothermic? This is exothermic. Actually, thermogram is consist of mostly two events. One event is your endothermic event, and another one is your exothermic. Endothermic event is the sample will absorb heat. That means more heat is supplied to the sample, and always the peak pointing upward. That means this is your endothermic. And in exothermic, opposite case. That means the sample will release the heat, and less heat is supplied to the sample, and the peak always pointing downward. This is that's all, and you can find the melting temperature from here, and this is for your crystallization temperature, and from here you can find the glass transition temperature, and the area under the curve will give you the enthalpy of the given sample.